So good afternoon, everyone. Thanks for joining us hybrid mode of the GW4 Water Security Alliance webinar seminar. So today is our very first time we have this kind of hybrid mode in Exeter. So campus, we have the another one in Cornwall campus, but this one is in Streatham campus. And we have Dr. Khoury. He's going to share what he's been doing in the ongoing European project NextGen, who just he's developed a serious game, and he would like to share with you and invite you to play with us about this serious game. So, as he said, there is some pre-games questionnaire. So if you are able to fill that, that would be very helpful. And then I will going to share you the link about this game itself, and if you can play with that game as along when he is talking, this will be also very useful, and then you can ask him the question right after that. And so there will be a post-game questionnaire to see how this change, you have changed your ideas, your thought about this serious game. This topic is about circular economy. So that's the purpose of this game, enhancing the people's understanding about the circular economy. So we would like to have maybe start this presentation.
Thank you. Thank you all for attending. Those which are here in person, as well as those which are here online. Type NextGen Serious Game in one word, actually. And you have the second link that happens, something called Toy Town. And that's actually, you can access directly the game from there. So it's not too bad. Second link from the NextGen Serious Game, search on Google. So right, once you've done that, you will arrive on that page. So let me minimize a bit some of this fancy annoying thing here. Okay. So we've got different serious games based on the same engine, and I'll ask you to go to the NextGen Serious Game, Horizon 2020, which is the one with the generic Toy Town Serious Games. We've got several case studies, Athens, Costa Brava, which are going to be active soon. But at the moment, we will only play with the Toy Town version, which is a virtual catchment with a population of approximately 300,000 inhabitants. And it has some fairly generic settings, and it's a combined sewer kind of setting. So if you click on that link, you will be redirected to some sort of introductory page with all sorts of material, pictures, explanation. But if you go to the very bottom, I will cut through all that because, well, I'm here to present, so I'll take you through it. Go to the business as usual game case. And once you click on that, there is a link at the very top in blue. Click on this link. It's written at the very top to open the business as usual game. If you click, therefore, on that link, note that at the bottom, you've got all sorts of videos and tips and things like that to help. But if you click on that link, it will directly start the game. Note that there is a general message. If you close that message, then you access the game interface. So what do we have in front of us? This is Toy Town. This is our virtual catchment. It's made out of interconnected components. First of all, in the top right, you got your main reservoir, which is alimented by rainfall and river flow. Oh, one more thing, I'm not an actual water specialist, so if the way I formulate things is not right, please forgive me in advance for that one. Okay, so the water from the reservoir is abstracted to the town. It goes to the drinking water treatment plant, and it's then redirected to 3 different groups of households. The little monopoly houses represent actual neighborhoods. So not just one house, but a whole group of them. Note that you can change here by activating the slider. You can change the percentages of houses in the neighborhood. This way you can add different kind of technologies for water reuse in different neighborhoods of different size and see what would be the effect if you combine different types of technology inside different neighborhoods in your town. Once the water is used by the household, it becomes wastewater and it's redirected via the brown arrows to your primary wastewater treatment plant. And afterward, well, it goes downstream in the river. So we got a couple, I mean, more than a couple, but some important indicators on the game. I'll go there quickly. The main reservoir stress to the top right, if you click directly on the icon, you'll have all sorts of explanations and view of what's happening. So there is a simulator that works in the background that simulates on a daily basis what's going to happen for the next 20 years, depending on the decision you're making. You've got the result in under 1 second, depending on what you change or modify. So the main reservoir stress is we take, for the next 20 years, we look at the level of the reservoir every day for each year. And if for 1 year, there is more than 10 days during which the reservoir is less than half full, then we consider it a stressed year. It's a bit of a, we just decided to make a decision how to decide the reservoir was stressed, and this is what we came up with. Similarly, we got the water demand met, which is we look at the percentage expressed the number of years over 20 years, during which if there is a year for there is 10 days during which the reservoir is nearly empty, that means you can't satisfy the water demand for your town. So if you can't satisfy the water demand for that year, therefore your percentage of water demand met will go down. We also have an indicator of environmental flow, so that's the amount of water left in the river once you've abstracted the water for the town, and it will define the health of your aquatic ecosystem in the river. We also have some pollution index indicator, which are about water quality. So we estimate, if I click on it, you would actually see the detail of how we do that. We basically look at the number of untreated discharge, of the number of water of water discharge of untreated water, which happens during each year, and we evaluate the amount of chemical oxygen demand, some sort of cumulative chemical oxygen demand that starts rising. And this cumulative depth of oxygen that is created because you start, dumping nutrients in the water is what we mean by pollution index. Okay. The goal of the game is quite simple. You got the circular economy score at the very top, and you just need to maximize it. So you think, well, not much going on, but if you click on circular economy score, this is what it's made out of. It's made out of lots of different parts. First, there's a water health score at the top, which in itself, it takes into account if you manage to satisfy the water demand in your town, the stuff I just showed you a minute ago. Also looked at the reservoir water health, which is the inverse of the reservoir stress. And you look also as the amount of water reuse you do in the household. I'll get to that in a minute. You also have an energy health score, which is based on, your energy footprint overall, and also if you manage to reuse materials from the wastewater, and if you do some biogas generation from the wastewater treatment. There is a material reuse health score, which we just look sheerly at the quantity of nutrients and metals you could potentially recycle from wastewater. There is an environmental health score, which takes into account, the amount of emissions saved because you save energy in your system, but also the environmental flow that was described earlier, and the water quality, which is referred by our pollution index. So there is finally a financial health score, because it's about circular economy, and therefore if you've got no finance, there's no economy. So we had a little something there, which is the overall, affordability of all these water components you can play with in the system, and then also the return on investment of two important technologies if you install them, which is the rainwater harvesting and the grey water reuse technologies. So you can click on the left top button, the blue button, and you can, there's different buttons there that you can click on and to change different things. For example, you can decide to click on population. You have a population of 300,000 inhabitants, but what would happen if you double your population? What happens to your system? So if you look at the reservoir stress, you stress 90%, you meet 100% of your water demand, and your pollution is 29%. So I doubled my population, which is not really a crazy situation, might happen. And once I double it, lots of stuff goes red. You only meet 30% of your water demand, your reservoir is stressed 100% of the time, and your pollution has shot up from 29% to 44%. So the system is on edge. Water is not an infinite resource. And as soon as you increase your population, you will see that it's under stress. So I will, you can refresh. If you want to go back to the default setting of the simulation, for those of you which are playing the game or which are online, you can just refresh by clicking the button, the browser refresh button, and it will work fine. One more thing, the game is compatible with most modern browsers. So Firefox, Safari, Microsoft Edge, and Chrome. If you use some other browser, I cannot guarantee the result. And there is also a possible problem if you're located behind a firewall, which intercepts the game communication and doesn't let it go. So if you are located in China, it might be problematic. Also, I'm not sure, but in some companies, sometimes they block traffic with their firewall. Let me quickly look at the chat, because there is a chat here. If there was any questions, okay, the links is visible for the game, so that's good. All right, so let's start. Let's get started. There is a series of questions that we can explore by playing the game, and this is what we're going to do together. The very first question that's usually is asked from the participant is the following: is using rainwater harvesting in household more efficient than using grey water reuse to reduce water stress in the town reservoir? So our water stress is 90%. If we click on the button here, we can access the neighborhood A, which has 100% of the house. So whatever modification, whatever technology we implement, we'll just do it at the level of the neighborhood A. So if we click on neighborhood A, there's lots of stuff we can change, to types of toilets, all sorts of things. But you can, here you see there's rainwater reuse, rainwater harvesting technology, and there is grey water reuse. So let's click. I invite you to click on rainwater reuse. I'll do it as well at the same time for those which don't have a laptop. And observe your reservoir stress is 90% and your pollution is 29%. If you use rainwater harvesting and you click on it, you'll notice that your reservoir stress goes down by 60% and your pollution goes down as well. So what is happening there? In the context of rainwater harvesting, you've got tanks which are installed inside different houses. And these tanks, they take some of the rainwater. This rainwater is partially treated and used for different usages in your house. So, for example, for gardening or toilets and things like that. Now, what's happening is normally when there is a heavy rainfall, you've got a lot of runoff water that comes all at the same time to your wastewater treatment plant. So what would happen is the wastewater treatment plant is overwhelmed and lets some untreated water go. But if you have in every houses in your town rainwater harvesting tanks, you actually take some of that rainwater. So it absorbs some of that rainfall and therefore it has a dampening effect. So you do not have as much of a wall of water all coming at the same time to your wastewater treatment plant, and therefore that's why the pollution goes down when you use rainwater harvesting. Now, I invite you to have a look, unlock rainwater reuse. I mean, just turn it off. And this time, for those of you which can access the system, use gray water reuse and see what is the difference. So with rainwater reuse, our water stress was going down to 60% with a pollution index of 16%. What happened if you deactivate rainwater harvesting, and this time you activate gray water reuse? For those which are online, or anybody in the room, I mean, if you click on the stuff, you'll notice that your main reservoir stress, if you use gray water reuse, will go down significantly, only 15% in that particular case. But you'll notice that your pollution stays up from 29%, it only goes down to 25%. So it's not really that helpful. It consumes less water and produce less wastewater, so there's a bit less pollution, but it doesn't have the same pollution reducing effect as using rainwater harvesting. So this answers the first couple of questions, which were about what's the difference between these two technologies, roughly speaking. Now, another question is what is the relative importance of the wastewater treatment energy footprint compared to the households when they have water-related device? Now, that's an interesting point, because if you click on the energy icon at the bottom at the wastewater treatment plant, you will get, if you first refresh the simulation, click the refresh button. So you start from scratch. And then you click on energy, and then you will see here what is the percentage of the energy footprint for wastewater treatment. It's around 2%, and it's around 98% from households, just for water-related device. So what comes out of it is there is a strong potential to save energy if you install energy-saving device or water-saving device in your households, because you can save on 98% of the energy footprint. Well, if you save on the wastewater treatment, it's important, but you save on 2%. So there's a strong incentive to communicate with households, because that's where most of the savings can be done. Another element is we look at the reservoir, and I'm going to reset the simulation. If you click on the left button at the top, there is a button called water management. So if you click on water management, you've got access to all sorts of parameters you can change about the reservoir. So what happens is the reservoir is a control system. It has a baseline river discharge, and when the reservoir is not stressed, when it's not half full, you let by default 80% of the water of the reservoir go to the river. It also has a stressed river discharge. If the reservoir happens to be stressed, less than half full, then you will only let 40% of the water go to the river, because you want to make sure the reservoir is always filled enough in order to supply the town. Now, you got an environmental flow of 75.8%. So you would think, if you want to maximize your environmental flow, well, how would you do that? You can just increase to the maximum, or to, let's say, 95% your baseline river discharge. You would think, well, that's the most logical step. So for those of you which have access to the game, please slide the baseline river discharge to 95% and see what happens to your environmental flow. And tell me what you observe. Yeah, Now, this is strange, right? Your environmental flow, sorry, your environmental stress goes up, but your environmental flow, does it go up or does it go down? This is what you're supposed to look at. It goes down. And this is weird because you open your baseline reverse discharge, you put it to 95%, so you should put more in the river. So why is the environmental flow going down then? That doesn't make any sense, right? But you are in a control system. And as such, as soon as you open quickly your baseline river discharge, the reservoir empties super quickly. Then it gets into stressed mode because it reached quickly the point where it's half full. And then, because it's in stress mode, it's gonna start getting into only leaving 40% of the water in the river. So it's gonna get up to halfway, but then it will again discharge at 95%. So it will oscillate at the half point level of the reservoir and goes between stress, not stress, stress, not stress. And because it's a control system, you end up with more, with an environmental flow, which is lesser. So the one lesson that we found about that kind of control system is you can't just min max value in order to increase, let's say, your environmental flow in a control system. You need to find where is the sweet spot, where is the set of value that really, for the particular setting you have in your situation, maximize things. So the just put everything to the maximum, everything to the minimum is not a strategy that will work in this kind of environment in the long term. Another aspect, it's what would happen to the overall energy footprint and water quality in the river if you were to connect 20% of the household to a decentralized wastewater treatment plant. So what happens is, I will refresh the game. You start in your normal state and you can select neighborhood B with the slider, get it up to 20%. So you got a neighborhood with 20% of the houses. Then with the button, you select neighborhood B, and then you're gonna go to the very bottom, and there is the possibility to connect it to a decentralized treatment plant. The decentralized treatment plant is a smaller unit, and it can process up to around 20% maximum of the amount of wastewater. What happens is it's usually located nearer from the household. So there's a lesser distance than the main primary wastewater treatment plant to go. It also does not necessarily, it doesn't necessarily do a full treatment. Sometimes it does a partial treatment, but it's located nearer. So that's basically how we set it up. So it's not fundamentally super new technology or anything really radically different. If you click on your decentralized treatment, you'll observe your pollution goes down slightly. So I'm going to click on that. You'll observe that from a pollution of 29%, you go to 27%. So that's not really an extraordinary phenomenon or anything. It's kind of small, but it's just that because it's decentralized, it's at different points of the river. So it's not, it doesn't discharge always in the same big point downstream. So there is not, there's more of a dilution effect in a sense. This is less concentration of discharge of untreated water in the same point. So there is that effect. But the other point, and I'm gonna show you this in the energy, which is if you look at the text here, there's something about pumping wastewater. So if I only use the primary treatment plant, primary wastewater treatment plant, you need to go further away to get your wastewater treated. It's usually far away. And there is a gain, usually, that depends on your situation. You could always set up something different, but we're trying to think of something fairly generic. If you activate your decentralized treatment, instead of spending 17,000 megawatt hour in pumping that wastewater, you will spend 15,000. So that will lower your energy footprint slightly. These are small gains. Yeah, we are not taking also assumption that there are fundamentally super different technologies at play. They are comparable. It's just one, okay, is a bit more efficient because it's a bigger scale, but overall the distance, yeah. Another question that we look at is the role of sustainable drainage system. So what would happen to your town if you connect all the neighborhood A house to a sustainable drainage system? So if the runoff goes through a sustainable drainage system, so you go to neighborhood A, you go to the bottom, and you switch or activate the sustainable drainage system and look at what changes the most in the indicators that you can see. So please activate sustainable drainage system and check what exactly does it change the most. Pollution, exactly. That's the biggest effect. It's a bit like the rainwater harvesting having tanks, except that it's more like a basin or a reservoir that will dampen rainfall. So you will have less water coming all at the same time in your wastewater treatment plant. What is interesting is it's an efficient technology to improve water quality, but it's also very good if you combine it with another technology, which is gray water reuse. We have seen before that gray water reuse was great to reduce water stress, also quite expensive. That's another aspect of it, but I'm not going to speak about that. But at the same time, it didn't do much for your pollution, for your water quality. But if you were to combine the installation of gray water reuse with sustainable drainage system, then this combination seems a bit like a winner item between this pair. You get some lowering. One last aspect, which is you can recycle nutrients and metals from wastewater. And what came as the most exciting, if I may say so, aspect of the project was that if you, let's say we restart the system into its default mode, and I click into material reuse. And when I click on this icon, you will see in blue what would happen if you were to recycle 85% of the nutrients that pass through the wastewater treatment plant. And we've made some sort of equivalence and calculation. So because you don't have to mine and refine these nutrients from scratch, this would be for this town of 300,000 inhabitants, the equivalent of, in energy saving, of having around like 8 wind turbines working full-time 24 hours the whole year. It will also be equivalent in carbon in carbon sink equivalent. This would be the equivalent to planting around 5% of the surface area of the Netherlands in forest every year, just if you recycle around 85% of the nutrients. There is a little also evaluation in the market value, but it's not very interesting, in the sense that nutrients are kind of abundant, and there's not much of a case for recycling them in comparison to metals. Now, metals is the bit that is a bit surprising there. We got, if you were to recycle, there's a list of metals in the table. So you could see aluminum, antimony, all these things. And there is the exergy that you save if you manage to recycle metal. So by exergy, you don't need to, it's a form of energy you don't need to spend. That is to say, you don't have to go mine the metal in the earth core, you don't have to refine it, you don't have to treat it. So you save a lot of energy if you can recover it. What is shown here is only domestic wastewater. So if you were to recover 85% of this list of metal, it would be the equivalent in energy that you would save in exergy, we save, of having 7 wind turbines working all the time, and like planting in carbon sink 5% of the surface area of the Netherlands. But what is interesting is if you were to add industrial wastewater, the concentrations. Yes, I have a question. No, I'll come to that. I went to Aquatech and I had a long walk in the different booths to find one place where they would do that, and there was no such things. Yeah, I'll get to that in a minute. But yeah, if you consider industrial wastewater, then the concentration of metals in there are 10 to 10,000 times more than just domestic wastewater. So you could easily do the equivalent if you were to recycle 85% of, industrial and domestic wastewater. You could easily, for a town of 300,000 inhabitants, in carbon sink, do the equivalent of planting 50% of the surface area of the Netherlands in forest every year, just by recovering these metals. Now, the interesting bit is as well, you don't need to recover all these metals. Actually, if you look at the very bottom, I've got an indicator. If you change, for example, just the aluminum, you only recover 85% of the aluminum. Just the aluminum by itself is like planting 1% of the surface area of the Netherlands forest. So there's a list of 8 metals that have most of the exergy. So if you manage to find a technology, and that's where we're coming, to recycle, metals out of wastewater, just concentrate on these 8 or 9 metals, and you will save a huge amount of exergy and therefore carbon emission. So that is all I wanted to show you for this fairly short presentation. There's a lot more that can be seen through the game, things linked to cost, things linked to all sorts of other technologies, and how, for example, if you install in household just things as as small as, for example, a new shower head, how you can actually impact massively the water consumption in your town and also the energy consumption. So, for example, things like if you look at your energy footprint, so far 618 gigawatt hour per year for the household, and 12 gigawatt hour for the main wastewater treatment plant, right? And if I was to install in every house, instead of a normal shower head, a fog shower head that just is a fancy shower head that mixes air and water, something like that. So if I just do that, then from 600 you go to 400 gigawatt hour of energy savings. Now that's a huge saving, and it's it's quite so there is a lot that can be done by just changing everything that you can find there, the type of toilets, the type of sink, the type of garden, spray and all this, and a lot can be investigated with the game with that. So thank you for your attention. For those of you which have access to the internet and a laptop, please fill in the post-game questionnaire. So I'm going to put the link in the chat so you can have access to it. It's very important, because if we can have the pre-game questionnaire, we can't really work if we don't have the post-game questionnaire result as well. So we can actually make a comparison with what playing the game did to how you answer the questions. So I will put in the chat right now. What's this? Yeah, sorry, on the top. Yes, you're right. Okay. So is this just a game, or could council actually use this to make decisions around upgrading wastewater treatment plant? Well, it's an interesting question. It's just a game, but you could use it to understand some of the basic dynamics, some of the things, some of the decisions you should or should not do in some generic case. For example, that some combinations of technology are going to help you. Things like rainwater harvesting are definitely quite helpful, or even the use of sustainable drainage system. But at the same time, you can't really have the exact output you wish for your particular case, particularly things like the river flow, for example. Every river is different, and the way the pollution might be amplified by the geographical situation, or the fact that you got industries in this area, or you don't have any industries in this area. These are, so it can be used, I would say, to help people to make decisions by informing them, but not be used as an oracle of some sort for their particular case, if that makes sense. Yeah. So is the model scalable downwards? Say it's a small town. Yes, it is. We actually started the model from a small town, from a micro case study, which was based in the Netherlands. So we used something from the KWO Water Institute called UWAT as a starting point to model, and it was like a super local study for a neighborhood. So yes, it's quite easy to scale down, and for that matter, to scale it up even better. It's a modular modeling system, so we can add bits to it to make it more fitting to a particular situation. For example, we can add an aquifer management module to the model, or how do you call that, a desalination plant, to make it more Mediterranean. And that's actually where we're going next. We have a Costa Brava case study coming. Yeah.
You mentioned money.
Yes.
I have a question.
So only for specific technologies. We got some overall costs for capital and maintenance for things like, for example, sustainable drainage systems. It's also scaling with the depth, the size, and all these things. We also have, if I click on a particular neighborhood, we do have a detail of the cost, return on investment, based on what is your water bill, and also what you could gain by installing, let's say, rainwater reuse. So if I click on rainwater reuse, then you got here, you know, a detail telling you how much and what's your return on investment. For here, it's under 20 years, so it's good. But if I was to use greywater reuse, the big problem for greywater reuse, and I'm going to activate it, and you can see, well, infinity years. You're never going to get your return investment with the present parameter unless you change the operational cost of your greywater reuse, if you manage to do an economy of market or something like that. So if you change the operational cost to 0.10 euro per household, then you should, and your initial thing, it should gives you something better. Now, I'm not seeing anything right now, so I'm wondering if I'm on the right thing. Yeah, I've got a little problem with my operational cost. For some reason, it's just gone down the drain, literally. Oh, it's because I'm using rainwater. Yeah, I wasn't changing the right place, so that's why it wasn't changing. So if I change my, yeah, that's it. If I change my, that's why it wasn't working. Change my greywater reuse operational cost, and I bring down the initial installation cost, I can get under 20 years, but it's not easy. And it seems that this technology also, it seems quite efficient so far. From a cost point of view, it needs some improvement from both sides.